Reflection is one of the fundamental transformations in geometry. Understanding how reflections work is essential for mastering geometric transformations. A reflection is a transformation that flips a figure over a line. This line is called the line of reflection, and it acts like a mirror. Let's start with a simple example. Here we have a coordinate system with a point A at coordinates 2, 3. When we reflect this point over the x-axis, the x-axis becomes our line of reflection. This line acts like a mirror. The reflected point A' has coordinates 2, -3. Notice how the x-coordinate stays the same, but the y-coordinate changes sign. A key property of reflections is that both the original point and its reflection are equidistant from the line of reflection. Both points are exactly 3 units away from the x-axis. Now let's explore the key properties of reflections using a triangle to see how entire shapes behave under reflection. Here's our original triangle, and we'll reflect it across this vertical line of reflection. When we perform the reflection, we get the reflected triangle. Notice that the reflected image is congruent to the original. It has exactly the same size and shape. The 2 key properties of reflections are: first, the reflected image is always congruent to the original, meaning same size and shape. Second, every point and its corresponding reflected point are equidistant from the line of reflection. Think of the line of reflection as a mirror. Just like when you look in a mirror, the reflection shows a flipped version of the original, but everything appears at the same distance from the mirror surface. Understanding these basic principles of reflection will help you work with more complex reflection problems and recognize reflection patterns in geometry. Now we'll learn how to perform reflections step by step. The process involves measuring distances and creating mirror images across reflection lines. Here are the 5 steps to reflect any shape. First, choose a point on the original shape. Second, measure the perpendicular distance from that point to the line of reflection. Third, mark a point on the opposite side of the reflection line at the same distance. Fourth, repeat this process for all key points of the shape. Finally, connect the reflected points to create the reflected image. Let's start with reflecting over the x-axis. The x-axis is our horizontal line of reflection. Here's our original triangle above the x-axis. When we reflect over the x-axis, the x-coordinates stay the same, but the y-coordinates change sign. Watch as we measure the perpendicular distance from each point to the x-axis, then mark the reflected points at equal distances on the opposite side. Now let's work through a specific numerical example. We'll reflect a triangle with vertices at coordinates 1, 1, 2, 3, and 4, 1 over the y-axis. Here's our original triangle with vertices clearly labeled. When reflecting over the y-axis, the y-coordinates stay the same, but the x-coordinates change sign. The reflected triangle has vertices at -1, 1, -2, 3, and -4, 1. Notice how each x-coordinate became its opposite, while y-coordinates remained unchanged. Finally, let's see reflection over the line y = x. This diagonal line creates a different type of reflection where coordinates swap positions. When reflecting over y = x, the x and y coordinates swap places. A point at coordinates a, b becomes b, a in the reflection. Reflections have many real-world applications. They create symmetry in art, architecture, and design, making objects visually pleasing and balanced. Reflections also create optical illusions and are fundamental in understanding how mirrors work. They help us analyze symmetry in nature, from butterfly wings to flower petals.